Okay, I was working my way through this code, and so I had described what phi was. Here it's actually using the, what is that? That is phi, right? Yeah, there's a couple different ways of writing the phi variable. Let's see if I can find what I'm looking, the two different versions, by inserting a special character. It comes up with special characters. I'm looking for a letter, in particular a Greek letter, I believe. And here it is down here, the curly phi versus the regular phi symbol. So that's also down here, the curly epsilon, which is in LaTeX that's a var epsilon and var phi instead of curly. And what other variables do we have here? We've got an r variable, a k variable. How is r used? R is used as a radius. That is probably related to, this is the cone, the shape of the cone. H and k are the center of the cone, and then by taking h plus the radius of the cone times the cosine of theta, I get the, this is, I guess, the initial position of x. And here we have y initial is the y coordinate of the y coordinate plus k, and k here is 2. So this is y. So this gives the initial coordinates of the circle. X equals 1, y equals 2. Let's see if we can see that in the in this diagram. Probably it's kind of difficult because where's the t equals 0 point? Okay, here's the way you would look at it. Here's the 0, 0 point right here, and the initial position. Not sure exactly where it starts, but x is over this way, y is over this way, I believe, so that the circle would start somewhere over here at time 0. And then you'll notice I actually calculated the initial time. Time initial is negative x initial squared plus y initial squared, or the square root of that. Why did I do it that way? I don't remember exactly, but it probably had something to do with fitting it into the cone nicely, so that the cone and the cylinder would have a good intersection. So, for instance, the t equals 0 point is right here. This would be the time 0 point, and this initial position here represents the position of the object at t minus that, well, at the initial time when that object was right there. So the initial time isn't t equals 0, it's some earlier point in time, when the point in time where it was at that point, where the circle was at that point in space, or the center of it at least. Okay, so now let's look at this matrix operation here. You'll see that what this thing does, it does a parametric plot, a 3D parametric plot of a Lorentz transformation of coordinates ti of theta, xi of theta, yi of theta. What is ti of theta, xi of theta, yi of theta? Well, this is letting theta go from 0 to 2 pi, and ti of theta, xi of theta, and yi of theta just represent this well, it looks like it represents this cone. I'm sorry, cylinder. This is the equation for a cylinder, right? Or is it? No, I don't think it is. If what would be this is the equation for a circle. This is that. Okay, so this G2 is representing that little circle right there. So I'm explicitly filling in that line, which represents the intersection between that cone, this cylinder, and this cone. Don't know how to. I would not be proficient at mathematics enough to give a closed form expression for that, but I'm able to kind of say that. So this is a specific point in time in the original. This is a specific shape of a circle in space at a particular point in time. And so what this does is it applies the Lorentz transformation to the locus of points on that circle. On the other hand, this graph is the cylinder. It has the same r cosine theta plus h, so that's right there. It has the same r sine theta plus k, that's right there. And then it just allows a second variable to go. So this parametric plot, notice, is different from this parametric plot. This parametric plot has only one parameter changing. But the second, or G1, I guess it's actually the first, but it has both t changing and the theta changing. Okay, this is actually two different plots. It's doing Lorentz transformation of this, which is the Lorentz transformation of the cylinder. Notice the radius is unchanging here. The x variable is just r cosine theta. The y variable is r sine theta. On the other hand, this part is the cone, and the cone, its radius changes over time. So the radius is t cosine theta and t sine theta, and its height is t. So this is the cylinder and this is the cone, and both of them, for both of them, it takes two variables, t going from the cylinder bottom, which is negative 25, and it allows theta to go from 0 to 2 pi, which goes around the complete circle to show the surface. And then this part is kind of let's see, labor intensive for the Mathematica program, and it's doing many calculations over the course of this animation to turn every point that would appear, like, let's go ahead and draw the non-Lorentz transformed version of this. As a matter of fact, I could just copy and paste this. Let's do that, and get another graph of it just by deleting the Lorentz transformation out of here. No LT dot. That should do it, and it will just give us. Why do we have? Oh, we need that manipulate in there. Okay, manipulate, and so we don't need. We just remove the LT. Don't know why that doesn't need to be inside the manipulate statement anyway. But anyway, let's look at that. What if okay, it would be the second one down here. So, oh, oops. It's not showing us the cone at all. Let's see what happened. I need to manipulate H and bring it over into the area where we can see it. So, so this is essentially what the graph would look like without, if before the Lorentz transformation. Notice that the Lorentz transformation has no effect, really no effect on the cone, but it does have an effect because this is the light cone, and kind of the idea behind a Lorentz transformation is it allows you to change an object's velocity without changing the speed of light. So when you modify the speed of the observer, basically you would make the cone appear to be moving, but you make the cylinder, the object will appear to be slanted in the space-time diagram because it's moving across the surface, but the cone itself will not. So the reason this H is the initial position of the cone, so it's not really changing. I'm not really changing the velocity here. I'm just changing the initial position of the cone, rather. So you can also see that if you view this from any angle, it comes out vertical, or you can see that it comes out as a perfect circle from, as long as it's not moving. It's when it's moving, it comes out kind of as an oval, either a contracted oval, or over here it's an extended oval.